Everybody. I've got another example for you where something a little different is going to happen. Let's see how this goes. We want to evaluate the definite integral, the improper integral, from 1 to infinity of 1 over x dx. What we mean by that, and you do need to write this just like this, we mean by that the limit as b goes to infinity of the definite integral from 1 to b of 1 over x dx. Now the antiderivative for 1 over x is natural log of the absolute value of x. Oops, I forgot my limit. Don't do that. Limit as b goes to infinity. Okay, and then the antiderivative for 1 over x is natural log of the absolute value of x. We're evaluating that from 1 to b. Now, because our x values are between 1 and b, these are positive x values. So I can take off that absolute value thing, because the absolute value of a positive x value is just the x value. So let's do that. Don't forget to write your limit notation with every step. It's not correct if you don't have that on some steps. Plugging in our limits of integration, then I'm taking the limit as b goes to infinity of ln of b minus ln of 1. Now, the natural log of 1, remember, is 0, so that can just go away. And I'm taking the limit as b goes to infinity of the natural log of b. What would that be? Let's remember what our natural log function looks like, which is something like this. It goes through the x-axis at 1. We're thinking of a b value that's greater than 1, but then we're letting that b value go infinitely far to the right. So what happens to the y values as we move along the log curve going to the right? Those y values go up to infinity. So back to evaluating our improper integral, the answer here is infinity. Now that's telling us something about the area under the curve. And remember, our definite integral was for 1 over x. So when we're thinking about areas, we're thinking about the 1 over x curve. Okay, this graph of the ln of x, I just put this here to illustrate why it is that I was about to say that the limit as b went to infinity the ln of b was infinity. That's all this graph was for. In terms of the definite integral that we're evaluating, the improper integral that we're evaluating, the integrand was y equals 1 over x. So this is the graph of y equals 1 over x. And what we just determined is that if you take the area to the right of 1 and you look at all of this area going infinitely far to the right, it never stops growing. In other words, you have an infinite amount of area. That's, with the area going to the right forever and ever. The accumulated area is infinitely large. So there's not a numerical answer to this improper integral. In a case like this, we say the improper integral diverges. And that means it cannot be evaluated. Now on the homework, it's going to say, evaluate each improper integral if it is convergent. If it is not convergent, write divergent. So what do those words mean? Well, if the improper integral equals a finite number, we say it converges or is convergent. And in that case, you're going to give the numerical answer. If the improper integral evaluates to plus or minus infinity, we say it diverges or is divergent. In that case, you can't give a numerical answer because there isn't one, so you're just going to say it's divergent. You won't know whether it's convergent or divergent until you actually evaluate it, though.